Yes, I record it when you're here.
What happened yesterday?
We only did like 5 minutes. Stop your whining.
What? You didn't work when I wasn't here yesterday? Why can't you not work today?
No, we worked and complained about stupid word problems.
Yeah. Alright, we're doing probability. And yesterday we started with the example of the spinner. I'm just going to write up here our probability formula. So if I have a probability of any event, basically we want the total number of outcomes over the favorable outcomes of what we actually want to happen. Now, how we get here is going to be vary depending upon the circumstance. So if I have two events, let's say probability of A or event B, and I say that these are exclusive events, meaning that they do not overlap in any way, I'm going to add the probability of event A to the probability of event B. So an example of this would be if I had 4 cards right here and I put them into a hat. Let's make it 5 just because. And I wanted the probability of an A or a C. Right? Well, I have one A and I have one C, so that probability would be the probability of A plus the probability of C. The probability of A is 1/5, and the probability of getting a C is 1/5. So I add those and get 2/5. Now we could have a more complicated circumstance, so we might have something like we have 2 of these A's right here, and then we might have a B, and a B, throw in a C, throw in a D, throw in an E. And we could ask the same thing now with this new set of cards. What's the probability of an A or a C? And again, we'll add those probabilities. Well, now I have 2 A's, so 2 out of 1, 2, 3, 4, 5, 6, 7, 8. 2 8s plus. I have 1 C, so 1/8 equals 3/8. So I go ahead and add those probabilities up. Or if I can count them, I can just go ahead and count them, and that's pretty easy. That's if they're exclusive. Mutually exclusive, meaning no overlap. So before I give you the next formula, I want us to just kind of do it with some common sense counting. Like we could count these probabilities without using a formula at all. And for this instance, let's say that I have a spinner, and we'll do a similar thing. I'll divide it into 6 sections. And let's say this is shaded, and this one's shaded, and this one's shaded. And then let's number them. 1, 2, 4, 6, 5, leave me alone, 3.
Wow.
What is wrong with you?
They're random. Okay, so let's do the probability of a odd number. Well, I have 1, 2, 3 odd numbers, right? Out of 6, so 3 6, and that's 1/2. What's the probability of an even number? 3 6, 1/2. See, 1, 2, 3, 3 even numbers. What's the probability of a white space? 3 6, 1/2. All right, so now let's talk about the probability of an odd number or shaded. Let's do it by counting. I know that I have 6 possibilities, right? Well, how many of them are odd or shaded? Well, this one's odd, and it is also shaded, right? It's both. But how many times will I count it? Once, right? This one's neither. This one's shaded, right? But it's not odd, but it is shaded. That's neither. This one's odd and shaded. So my answer is 3 6 yet again.
The 3 is odd.
and odd. Thank you. So 4 6. And we get 2/3. You mean this?
Oh, you're using
No, you can use it.
You can write on the board.
But then Savannah would be sad.
She doesn't care.
Yes, she does. All right.
I want to learn this. She says it's crappy.
So let's use the formula. Now the formula of probability of A or B that I gave you says probability of A plus the probability of B. Well, what's the probability of event A? Well, that we have an odd number, which we've calculated is 1/2. Just for ease, I'll say 3 6 so that we have like denominators. In the probability of event B, shaded, we also calculate, well, we didn't calculate that, but we can see probability of shaded is 3 6 right here. 3 6, and then we add those and we get 6 6, which is 1. Wait a minute, these are two different answers. This formula, the way it's written, is for exclusive, meaning there is no overlap. So this formula will not work in this case. We need a new formula. So here's our new formula.
No overlap. What does that mean?
As in, the two events aren't... I'll explain in a moment. Here's our new formula. If we have probability of A or B, and these are not mutually exclusive, meaning there is overlap, we need to subtract out repeats. So we start the same way as the other formula, but then we subtract out the probability of both of them happening. Let me explain the reasoning. Here's the reasoning. Let's say I have a Venn diagram, and I list my two events. This would be the exclusive case. Exclusive. Event A is here, event B is here, and all the things in A are inside of here. A were the odd numbers, 1, 3, 5. And B was all the shaded regions, right? So I have all these shaded regions in here. No overlap. Okay? That's exclusive. But the reality of our spinner is actually that some of the numbers are on odd and shaded. Do you see what I'm saying? That means that there's overlap. So our case is actually like this, where we have some of our odd numbers, and in this case the 1 and the 5. 1 and 5 happen to be in shaded regions, and the odd number 3 is over here. So event A, event B, and then I have one shaded piece. So that's shaded, pretend that's shaded, shaded. One shaded piece is a 4. Okay, so this is overlap. You getting this down, Ryan? You good? Okay, you better be good. So, Samantha, who has walked out rudely,
What do you want?
So we need to subtract out this piece right here. We need to subtract out this piece right here, which is the AND case, that both happen. So when we go back to our formula, the probability of event A is still odd. You know, probability of odd is still 3 6. The probability of event B, which is the shaded, is still 3 6. But I need to subtract out the probability that both of these happen. And that would be, in this case, 2 6. So I get 3 plus 3 is 6 minus 2 is 4. 4 6, which reduces to 2/3. Now, of course, in a situation like this, you could just count them out and not even deal with the formula at all. But more likely, you will have this. The probability of some event, A, is 1/2. And the probability of some other event, B, is, say, 1/3. Suppose I say that these are not mutually exclusive, meaning there is overlap of these cases. Now, I don't actually need the picture in order to do this problem, because one of our other formulas for probability is the probability of A and B happening, both, in which case I just multiply those two probabilities together. So, I go to my formula, the probability of A or B, if they are not mutually exclusive, is the probability of A plus the probability of B minus the probability of both happening. Well, the probability of both happening is when I multiply these two. So that's going to be 1 6. 1 times 1 is 1, 2 times 3 is 6. The probability of A is 1/2, and the probability of B is 1/3. Now I go ahead and do this. In order to do this addition and subtraction, I need a common denominator. The common denominator is 6. So I multiplied that by 3, multiplied that by 2, and now I continue. So 3 plus 2 is 5, minus 1, 4, 6. 2/3 is the final probability if they are not mutually exclusive. Now, if they are mutually exclusive, then I just add these and I don't need to worry about this extra subtraction. So that phrasing, knowing whether there's overlap or not, is very important. Now we can do this with decimals. So maybe the probability of event A is 0.1, and maybe the probability of event B is 0.15. And again, let's say they're not mutually exclusive. Okay, so I do probability of A or B. That's going to be the probability of A plus the probability of B minus the probability of A and B, both of them happening. So I add 0.1 to 0.15 and I subtract out their product. So I go ahead and I multiply those, 0.1 times 0.15, and I get 0.015. So I go ahead and add and subtract, going right across. And that is my final probability. Okay, so that's probability of mutually and not mutually exclusive events, or probabilities. Okay, as in I have two events and I'm going to find the probability of both happening. Now we have the probability of dependent and independent events. And this is and or then cases. So let's say I have a bag of marbles, and in my bag of marbles I have these marbles right here. Okay, so I have some blue marbles and some white marbles. Now, if I wanted the probability of a white marble on one draw, like I have them in a bag and I close my eyes and draw one, it's, you know, I have 8 marbles and 5 of them are white. And if I wanted the probability of blue marble, 3 out of 8, pretty simple. And there's no overlap here. The marble's either white or blue. No overlap, so mutually exclusive also. But what if I wanted to draw 2 marbles? Not just one. See, this is one draw, What if I want to draw 2 marbles? Well, that brings up a question. Do I replace the marble after I draw it, or do I keep it? Let's do if I replace it. So this is going to be with replacement. And you'll see that word often in probability, with replacement, meaning I draw the thing or the event happens and then I reset the stage. I put everything back the way it was and do another draw, another event. So then what's the probability of drawing a white and then another white? Well, I have 5 whites, so 5 eighths, and then times, I take the white marble out, I'm like, okay, I got a white, I put it back in, and now I draw another white. Probability of that event, so I multiply them. 25 out of 64. Do you understand how we did that? What if I did the probability of a white and then a blue? Well, I have, again, 5 white marbles. I get the white marble out, I look at it, it's white, I put it back in, and now I draw another marble, see if it's blue. There are 3 blue marbles out of 8, and then I just multiply these, 15 out of 64, and I'm not bothering trying to reduce these, I don't think they reduce. Any questions on how I got that? Now notice the difference between or and then. See, if I have an event and I want to see 2 different possibilities, that's an or case, then I have to ask, well, is there some overlap? And I have that formula where I add 2 things and then subtract. Then I just multiply the successive events. But that's with replacement. What if I have the same situation and I don't replace it? So I'm going to do 2 draws now, but without replacement. As in, I take the marble and I keep it. As in, I keep the marble. Well, that's going to change the number of marbles that are in my bag. So, what's the probability of a white and then a white without replacement? Well, I have 5 eighths. I take the white marble out. I see that it's a white marble. Now, how many marbles are in my bag? 7. And how many white marbles are now available, assuming that I've actually gotten a white marble? 4. So this is a dependent event. See, the previous incident was an independent event. This is dependent because the success of the first event changes the success of the next event because there's a different number of marbles available. So now there is some reducing here. I could cancel those and get 5 out of 14. Now I wouldn't do any reducing until after I've written this all out, and then I go ahead and cross cancel. So there's my event. Well, let's do the other one. Probability of white and then a blue. Well, there's 5 eighths that are white. Now, this is a little bit different. I have taken out a white marble, so how many white marbles are there? 7. How many blue marbles are there? 3. There's still, all 3 of the blue marbles are still in the bag. And no canceling, so 15 out of 56. That's the probability of that happening. Okay, let's say the probability of event Q happening is 1/4, and the probability of event R is happening is 2/3. What's the probability? Now we're going to assume that these are independent, meaning that one event does not affect the other. They don't affect each other. And they are not mutually exclusive, as in there is some overlap. So some events in R are also in Q, and some events in Q are also in R. So then what's the probability of Q or R? That's going to be probability of Q plus the probability of R minus the probability of both of those, Q and R. So I multiply Q, or I have Q as 1/4 plus R 2/3 minus, okay, I multiply those and get 2/12. My common denominator is 12. I could have reduced that, but that would have been wasting some time because my common denominator is 12. Now, I can't cross-cancel or anything because this is addition, subtraction. You can't do that. So we do this, and we get 9/12, which then reduces to 3/4. What's the probability of Q then R? Well, if they are independent events, then I can just multiply them, and I get 2/12, which is 1/6.
What happens if they are independent?
In that case, I'm not going to. In that case, we have to think like we did over here. Well, then how many is left? They affect each other somehow. Which I'm glad you asked that question, because that brings us to exactly that case. In which case, we're going to need a table. So let's say we have some girls in our class, we have some boys in our class, and some are left-handed, some are right-handed, and we'll have totals at the end. I like to do double lines where the totals go. And let's just fill in these. Let's say we're a small school, so let's say we have 5 left-handed boys, 15 right-handed boys. Girls are a little bit crazier. Let's say we have 6 left-handed girls, and we don't have quite as many girls, let's say, for whatever reason. Let's say there's only 9 girls that are right-handed. Yes. Yes. No, we are not equal. Just look at your hair lengths. Not equal discrimination. You have more hair than boys. Discrimination. You should cut off half your hair and give it to Ryan. That's
what Miley Cyrus did.
That's equal opportunity to have length of hair.
Hey.
All right, no, that's terrible. All right, so now down here we're just going to add. So we have 11. Does that make sense? We have 11 lefties, and then we have, if I add these, 24 righties. If I go across 15 girls, I go across 20 boys, and then how many people do I have now? When I add across here, or if I add down here, I should get the same number of 35. 35 people total in this school. Small school. Okay, anyways. What's the probability that I choose a girl? Well, there's 15 girls, right? So 15 out of how many?
35.
Which I could then reduce to 3/7. What's the probability of a boy? Now, you could do, we could do it 2 ways. 20 out of 35 and then reduce that, divisible by 5. But hopefully you see that we could have just said, well, 3/7 are girls, then 4/7 are boys, right? Subtraction. 7 minus 3, 4.
I know from that.
Unless we have some people who are neither boy nor girl, but we aren't going to consider that case. What's the probability of a lefty?
It's 11 out of 35.
And what's the probability of a righty?
24 out of 35.
Or we could subtract that,
Yeah.
right? Okay. Can we reduce this? Probably not. All right, now, what's the probability of selecting a lefty given that we know this person's a boy? Well, that means I'm only considering boys because for some reason or other I know that I'm choosing a boy.
Or the pancakes.
Do you understand what I'm saying? Well, I have 5 lefties out of 20 boys. So 1/4. What's the probability of it being a girl given I know that I have a righty? Well, I know I have a right-handed, right? You see what I'm saying? So this side right here, this is telling me that I know for whatever reason that this event has already happened. I have already gotten the righty, and I know it for a fact. Alright, so I have 24 righties to select from, right? And only 9 of them are girls. So I can reduce that 3/8. Okay? So we do need to table. We could also do this on a tree diagram, which we'll work on tomorrow a little bit. Now, here is our forecast. Your last assessment quiz is Friday. If for some reason you decide that you must have a dentist appointment during school or whatever thing, you have something on Friday, you need to go get your finger measured for a ring or some other dumb senior thing, and you're not going to be here Friday, conveniently during this class, but conveniently after lunch. You know, whatever.
I was here for lunch yesterday.
Anyways, if you are not going to be in class on Friday, you must do the quiz that is on Friday, Thursday, before you leave school. As in, before 3.
Today.
We are going to review / finish probability tomorrow.
Tomorrow is
This
Friday. Tomorrow is Friday.
tomorrow is Friday. All right, quiz tomorrow.
What?
So you must do your quiz today. Do we have class Monday? All right, so let's change all that. Let's change this. We'll change this. Quiz, listen, quiz Monday. Because Ryan's getting his finger measured for a ring or whatever silly reason he's not going to be here.
Graduating college.
Who cares about that? Your cousin only.
Family.
No. All right. So if you are not going to be in class on Monday for some reason, then you must take your quiz on Friday before school ends, before 3 p.m. And we'll use Friday to review all of probability that we have done. And then just so that I'm aware of your life, what's on Tuesday next week?
Nothing.
You know what? It occurs to me we can't do this because we have to have the quiz Friday because your grades have to be in before Friday, don't they? Yeah. So we have to do, so no matter what, everyone's going to do their quiz tomorrow before 3, but I think that you are going to want to review in class. Am I correct?
Yes.
Okay, so this, strike this, quiz Friday.
We have 5th hour free.
So 5th hour, you'll do your quiz, and then I'll grade it that same day and conclude your grades for pre-calc. So I guess there's no reason to even be in class next week because we aren't going to add any.
Days.
Yeah, we'll have a donut day next week or something on Monday.
Are you going to get them?
No, because we don't open till 7.
Can we please make up our mind when we're going to have this donut day?
I don't know, because Bernie's is
Tuesday.
never open at the right
I
time.
can go to the gas station.